depth. What would it be like to look around you within that world, where all you can make out is lines all within the same plane? That is a mind-bending exercise, good food for thought, regardless of whether it would really be possible for some kind of awareness to exist within such a ridiculously limited frame of reference or not. Over the next 9 entries, we're going to look at each of the dimensions from the 2nd all the way up to the 10th and see what kind of a mental castle we can build for ourselves, one brick at a time. Along the way, I want you to keep reminding yourself about something called the point-line-plane postulate, which uses the same kind of logic as the line, branch, fold of the Imagining the 10th Dimension project. This postulate is the accepted method used to imagine any number of spatial dimensions using the same repeating pattern. 0, a point. Whatever spatial dimension you're currently thinking about, imagine a geometric point within that dimension. Remember, when we say that this point has no size, what we really mean is that this point's size is indeterminate. Indeterminate means that any and all sizes you care to imagine, from the infinitely large to the infinitesimally small, are true for that point. Let's say that this is a point within dimension x. 1. A line. From the current dimension you're examining, find another point not within that dimension. An easy way to do that is to imagine the first point at its largest possible size within the constraints of its own dimension, and then ask where a different point would be that isn't encompassed by that first point in its infinitely large state. Once you've found a second point, draw a line through both points, and now call what you're looking at dimension x plus 1. 2. A plane. Again, think of both of those points encompassing their largest possible version within the constraints of the current dimension, and find a point that isn't part of what those 2 points are encompassing. Now you're thinking about dimension x plus 2. This logic can start from any spatial dimension, and it can be repeated infinitely. That is, once you've imagined dimension x plus 2, you can rename it dimension x and repeat the pattern as many times as you want. Here's an important thing to remember. If we're not assigning any meaning to the dimensions we're visualizing, there's no reason to stop at 10. However, with this project, by the time we've arrived at the 10th dimension, we do find a way to say that we have arrived at the most all-encompassing version of the information that becomes reality, or the underlying symmetry state from which our universe or any other patterns emerge from the breaking of that symmetry. And I do hope you'll enjoy the journey as we work our way through this logical presentation, one step after another. Imagining the 3rd dimension. Some people dismiss discussions of the 2nd dimension, saying it would be impossible to see something with no depth. What if I told you the 3rd dimension is also impossible for us to see? In my original Imagining the 10th Dimension animation, I said that imagining the 3rd dimension should be the easiest for us, since that's what we see around us every day. But there is a problem here. Most of us, when we imagine the 3rd dimension, also imagine energy, change, and life itself as being in the 3rd dimension. But how can any of these processes be part of the 3rd dimension when what we're talking about is space without time? In the remarkable television series Through the Wormhole with Morgan Freeman, physicist Julian Barber says this: "In my view of the universe, it's just like a huge collection of snapshots which are immensely richly structured. They're not in any communication with each other. They're worlds unto themselves. In some very deep sense, the universe, a quantum universe, is static. Nothing changes." What Dr. Barber is conveying here is that our 3D universe is like a giant flip book animation. And even though it feels to us like our observed reality is continuous, each of those snapshots he's referring to represents a frame of 3D space without time. Each of those frames is defined by the speed of light and Planck's constant, which is the smallest possible distance that can be observed, and the smallest possible duration that our reality can have before words like distance and duration lose their meaning. So the only way for change to occur is to string those snapshots together and view them from the fourth dimension, one Planck frame after another. There's a second problem with the way people tend to think about the third dimension. It's so easy to forget that it takes time for light to travel to our eyes. So even if we look at our own hands, there was already a tiny delay for the time it took for the light rays to bounce off our hands and arrive at our retinas. If we're trying to imagine the third dimension then as space without time, we're already imagining something that can't be seen. This is easier to think about when we move out to the vast distances of the nearby stars. If I'm looking in the night sky at a star that's 10 light years away, I'm looking at what that star looked like 10 years ago. I'm not looking into space, I'm looking into space-time. And right next to that star could be a different one that's 20 light years away. There those two stars are, seemingly side by side, and yet when I'm looking at one, I'm looking 10 years into the past, and when I'm looking at the other, I'm looking 20 years into the past. Isn't it amazing to think about how all the different distances of galaxies, stars, planets, and satellites that we might see through a telescope blend together into a vision not of 3D space, but of 4D space-time? And even though it's on a much smaller scale, the same is true if we look at our hands, then look at some other object that's further away. Even though our brains tell us we're looking at a 3D world, the time it takes for light to reach our eyes from any particular object will be defined by how far away that object is from our eye. And what we're seeing at any particular instant is really a blend of those tiny delays, a snapshot of 4D space-time. The next time someone tells you that the first and second dimension don't exist because something with no depth is impossible, think about how the third dimension has the same problem. In our minds, we can visualize objects that are constructed from length, width, and depth, but we can't actually see them with our eyes unless they have duration within 4D spacetime. Does that mean the third dimension doesn't exist? Of course not. But those 3D snapshots of space without time are much stranger than our intuition might tell us, because within each of those snapshots lies the potential for quantum entanglement, which can occur at any distance across the universe. Remember, those connections and superpositions are not just faster than light, they're instantaneous. As Julian Barber says, a frame of the quantum universe exists in a place where time doesn't exist. And if that idea seems unimaginably strange to us, perhaps that's because it's so easy for us to forget that you and I are really part of something larger than the third dimension. Imagining the fourth dimension. Here's where we start getting into some possible confusion because the same word can have many different meanings. When people say that time is the fourth dimension, what does that mean? The fourth dimension adds a way for the third dimension to change. This is obvious when we say the third dimension is space without time. But the entropy-driven arrow of time that people associate with this concept is obviously not spatial because it behaves in ways that are different from the first three dimensions. This is why some people prefer to say that the fourth dimension is a temporal dimension, while the first three are spatial. But the more we learn about space-time and general relativity, the more we realize that time is not just an arrow. The fourth dimension stretches, it bends, and quantum entanglement shows that it's possible for particles to make instantaneous connections within it, even for there to be causality in time's reverse direction. And as mind-blowing as this may be to fathom, the accepted definition for antimatter is that it's matter which is moving backwards in time. This is why, with this project, I prefer to call the fourth dimension duration. I ask people to accept that time is a direction, not a dimension, in the same way that up or forward are directions rather than dimensions. Two opposing directions can be used to describe a spatial dimension, and time and anti-time are two words we can use to describe the fourth dimension. But they're not the only words, and this is important because all we're really trying to do here is come up with words that describe the dimension which is at right angles to the third dimension. Here's something important to remember. None of these dimensions exist in isolation. You can't make a 1D line without using points. You can't make a 2D plane without lines. You can't make a 3D space without planes. And you can't have a 4D duration without multiple Planck frames of space. Saying the fourth dimension is duration makes no more sense than saying the third dimension is depth, if when we say those phrases, we're thinking you can have duration without space, or depth without length and width. Saying the fourth dimension is space-time, then, at least acknowledges that the fourth dimension encompasses the dimensions from which it is constructed, and doesn't exist in isolation from the other dimensions. Let me say this again. It doesn't matter what label you put on the fourth dimension, or any additional dimension, as long as you're thinking about how the new dimension is somehow at right angles to the ones before. A rose by any other name still smells as sweet, to paraphrase Mr. Shakespeare. So, time is not really a dimension, but no matter what dimension you're examining, the direction of time is a word we can use for tracking change from state to state. In Aren't There Really 11 Dimensions, I insist that it makes no sense to say that the first three dimensions are spatial, and the fifth dimension and above are spatial or, at very least, space-like, but then to say that the fourth dimension isn't spatial. If that were the case, then the mental castle we're building here has a very rickety layer at the fourth dimension, and the whole structure is prone to crashing down. Last entry, we talked about how it's really impossible for us to see the third dimension because it takes a certain amount of time for the light from anything in the third dimension to reach our eye. And that's just as true for our hand in front of our face as it is for a star 10 light years away. Saying that a third dimensional object has length, width, and depth is a phrase we casually say, but we have to keep in mind that discussing a third dimensional object like a cube is the same as discussing dragons or flatlanders. A 3D cube is an idea which we can freely discuss, but without using the fourth dimension to view such an object, it's only a concept. Likewise, persons who talk about tesseracts as being four-dimensional objects say that this is what the real fourth dimension is like. But what we're really talking about with a tesseract or any other n-dimensional shape is the same as a cube. It's an idea. In order for a tesseract to really exist, it has to have a duration within its dimension. And when we watch an animation of a rotating tesseract, we are visualizing how that structure could rotate and change from state to state over time when viewed from the third dimension. Likewise, just as a cube represents a simple and idealized shape within the third dimension, but there are the limitless range of other shapes that can exist within the third dimension, the additional degree of freedom afforded by the fourth spatial dimension allows for an even larger number of other shapes which can exist within that dimension. One word physicists use to describe the path an object takes within space-time is a world line. Another word for a fourth-dimensional shape, coined by author and futurist Bruce Sterling, is a spime. With my Imagining the 10th Dimension project, I ask people to visualize themselves in the fourth dimension as a long, undulating snake, which is a way to think about the data set that represents a person's length or duration within the fourth dimension, from conception to death. Do you see how that snake is a spime? Depending upon your point of view, though, that snake could be much blurrier than what we show in the original animation. Every day, our bodies are exchanging atoms with the outside world through the air we breathe, the food we eat, and the water we drink. A constant cycle of repairs and replacement means the spine representing a person from conception to death is a much more wide-ranging and interconnected shape than what we might first imagine. One of the 26 songs attached to this project, called Change and Renewal, is about this idea. Let's finish off by thinking about the point-line-plane postulate again, which can be used to visualize any number of spatial dimensions. The trick I've suggested you start with each time is to think of a point that encompasses the entire dimension, then find a point that is outside of what that first point encompasses. So a one-dimensional point, in the largest version of its indeterminate state, occupies the entire length of a line, and some new point not found anywhere on that line allows us to visualize the second dimension. A two-dimensional point, in its largest version, fills an entire plane, and a point not within that plane gets us to the third dimension. A third-dimensional point, at its largest version, is like a single Planck unit-sized slice of the entire universe, and allows us to think about the possibility that Julian Barber has pointed out, that each of those 3D frames allows for the instantaneous quantum connections often deemed as supremely mysterious and unfathomable. Having said that, though, we still have to decode the mystery of how we can have a physical world made out of objects that are not infinitely large within the third dimension. And this is why I say those quantum connections are at right angles to space-time. So let's continue the point-line-plane postulate's logic into the fourth dimension. A 4D point at its largest version would encompass the universe not just in space, but in space-time. The point would reach from the beginning to the end of the universe in the same way that a photon traveling at the speed of light would perceive itself to be simultaneously emitted from a distant star and arriving at an observer's retina. This is an important concept we looked at in Light Has No Speed. It also ties nicely to something Einstein said a number of times. There is a way of thinking about reality in which the separation between past, present, and future is only a stubbornly persistent illusion. What's outside that largest possible 4D point we've just imagined? Well, if you are a person who has been trained to believe that free will is also nothing more than a stubbornly persistent illusion, you might well say, that's as far as we need to go. After all, if the universe was set in motion at the Big Bang, and anything we do is an inevitable outcome based on what has come before, then the largest 4D point we can imagine accounts for all of that, from the beginning to the end, including the now that each of us is observing at this very instant. But what if you believe in free will? With this project, that's where we start to think about the fifth dimension. Imagining the fifth dimension. We keep returning to this idea. Every time we add a spatial dimension, we need to find a way to think about how the new dimension is at right angles to the ones that have come before. Another word for this concept is that each new dimension is orthogonal to the previous ones. Last entry we looked at how it makes the most sense to say that the fourth dimension is space-time, a dimension which enfolds length, width, depth, and duration, and to accept that the fourth dimension is spatial. Yes, as creatures who get their energy from chemical processes that obey the thermodynamic laws of entropy, we appear to be moving in only one direction within that dimension, a direction which we call time. But the evidence is strong that the opposite direction, anti-time, is just as valid and just as real. And having two opposing directions is one of the basic attributes added by any additional spatial dimension. So what's at right angles to space-time? It's interesting to read this quote from a lecture by Stephen Hawking. One can think of ordinary, real time as a horizontal line. On the left, one has the past, and on the right, the future. But there's another kind of time in the vertical direction. This is called imaginary time, because it is not the kind of time we normally experience. But in a sense, it is just as real as what we call real time. And it's interesting to think about this. One of the central ideas to this project's approach to visualizing the extra dimensions is Everett's many worlds interpretation of quantum mechanics, which explains how every possible outcome for our universe is equally real, but as observers we can only see one of those universes at a time. According to Everett's theory of the universal wave function, the reason we can't see any of the other universes is because they exist within a subspace which is orthogonal to the ones we are observing at any particular instant. But even though Hawking has talked about another kind of time which is at right angles to our space-time, and Everett has talked about the other parallel universes being orthogonal or at right angles to the version of the universe any one of us is observing right now, neither of them have said that these additional realms are in the fifth dimension. Why is that? Is this a failure of imagination from two of the most brilliant minds of the 20th century? Or is this a free will discussion? This is where my project's line branch fold concept for imagining dimensions becomes particularly useful. The fifth dimension, by virtue of being at right angles to all of the dimensions that have come before, gives us a way to get to those other connections of the quantum world and Everett's many worlds that might seem unimaginable from the viewpoint of someone who believes there's nothing more than 4D space-time. In 2007, a team of scientists at Oxford under the direction of David Deutsch published a new proof equating Everett's many worlds interpretation with the probabilistic outcomes at the quantum level and the parallel universes resulting from chance and choice. And New Scientist magazine declared this to be one of the top science news stories of the year. In 2010, a team of scientists at Oxford participated in a speculative art project created by John Ardern and Anab Jain as Superflux, the fifth-dimensional camera project. David Deutsch acted as one of the consultants on this project too, but of particular note is a video they created featuring Dr. Simon Benjamin, who is from the Quantum Information Processing Interdisciplinary Research Collaboration, the QIPIRC, based at Oxford University. Within this video, you'll see Dr. Benjamin show a diagram very similar to the ones from my project of branching timelines resulting from chance and choice, and he suggests that these are occurring at the fifth dimension. Einstein, another of the great minds of the 20th century, accepted the existence of the fifth dimension. He did take a while to get used to the idea, but in 1923, he eventually gave his approval to Theodore Kaluza's proposal that the field equations for gravity and light are resolved for our space-time when they're calculated at the fifth dimension. The fifth dimension then becomes a way to combine Einstein's theory of general relativity with Maxwell's equations describing electromagnetism. A few years later, with Oscar Klein's additional input, the resulting Kaluza-Klein theory would eventually become the starting point for string theory. But if we're talking about something that is at right angles to space-time, why can't we see it? Well, we've already talked about our mythical 2D flatlanders, who would be unable to perceive up and down because it was outside of the length and width of their 2D world. And we've also discussed that although we've been taught that the world around us is 3D, the startling fact is that the time it takes for light to travel to our eye means it's impossible for us to see the third dimension by itself. So asking why we can't see the fifth dimension may be like asking why we can't see the other side of a building as we stand in the middle of a street. It's not that the back of the building isn't there, or that it's impossible to see, it's just that we can't see it from our current reference frame. But the standard explanation for why we can't see the fifth dimension and beyond is because it's compactified or curled up at the Planck length. Since we've already established that our 4D space-time is not continuous, but is divided into 3D frames or quanta, I have proposed that it follows that our physical window into the fifth dimension is only one Planck frame wide, and the various aspects of our awareness can, as we saw in our opening quote from Winston Churchill, connect into the fifth dimension more fully. Make no mistake about it. With this project, I am insisting that we are really not in the third dimension, or even the fourth dimension. Our now is a moving point within a fifth-dimensional probability space, and I believe the more that people embrace this idea, the deeper their understanding of our reality will become. The analogy often used in string theory is to think of the fifth dimension as being like a garden hose stretched out on the ground. From a distance, the hose looks like a line, but up close we can see that the walls of the hose are curled up on themselves, so that if an ant were to walk inside that hose, it could go from one end to the other, the straight line of the fourth dimension, but be moving in a second dimension as well as the first. In my Imagining the 10th Dimension animation, I showed a Mobius strip and asked people to think about how a flatlander moving on this strip would feel like they were traveling in a straight line, but in reality they would be twisting and turning in the dimension above. This is useful as a way to think about the fifth dimension, but the garden hose analogy adds one further wrinkle. What if a fly were to enter our hose? Unlike the ant, the fly would be able to travel not just in a second dimension, but a third. So if our hose were 4D space-time, the ant would be moving in the fifth dimension, and the fly would be moving in the sixth. You and I, it appears, are ants rather than flies. But next entry we'll talk about how that's a good thing, as we move on to imagining the sixth dimension. Before we finish though, I want to mention one final thing. I was thrilled to read recently that well-known physicists Leonard Susskind and Raphael Bousso have published a proof equating the branching probabilistic outcomes of Everett's many worlds with the string theory multiverse. I'd like to give you a link to Sean Carroll's blog entry about the new proof, and also here's a link that was published at archive.org. And while we're looking at links, here's a Discovery Channel blog entry about a new theory analyzing black holes from the perspective of the compactified fifth dimension we've been talking about in today's entry. Imagining the sixth dimension. What's the difference between the fifth dimension and the sixth dimension? With this approach to visualizing the dimensions, that question comes up a lot. After all, if the fifth dimension includes every possible state for the universe which can be connected to the now any one of us are currently observing, why do we need to talk about anything beyond that? Let's pull out a piece of paper and ponder this question further. First of all, put a dot near one edge of the paper and label it the Big Bang. Likewise, place a dot near some other edge of the paper and label it the end of the universe. Finally, draw a line that passes through those 2 points and place a point somewhere near the middle of that line, which we'll label U. Okay, if that middle point represents U right now, then let's place another point nearby, but not on the line we've just drawn. Do you see how this point could represent some other version of you, such as the one where a childhood accident completely changed your life? Or even just the version of you that got bored with this entry and stopped watching 10 seconds ago? There could be a new line which extends from the Big Bang and passes through this alternate version of you, and each of those could be thought of as a one-dimensional line. But the only way the line for version 1 and the line for version 2 could be considered simultaneously is if we were to consider the 2D plane of that paper we were drawing on. In fact, we could place another point earlier on one of the lines and say that it represents your moment of conception, and then imagine an array of possible lines representing all of the versions of you that could possibly have existed from your moment of conception onwards, and they could all be contained within this 2D plane. Now let's think of a different point, but in this case let's imagine that it's floating a few inches above the paper. Perhaps this new point represents the version of the universe where dinosaurs never became extinct, which would mean that you, as we know you, wouldn't even exist on that line. We can imagine a one-dimensional line that passes through the Big Bang point on the paper and this new point. We can imagine a different 2D plane that passes through our first or second line and this new dinosaurs line. But here's something important about what we've been visualizing. The only way we consider all three lines at the same time is by using the third dimension. I hope it's obvious by now that the point-line-plane postulate tells us the logic we've just used to think about the first, second, and third dimension is directly translatable to the fourth, fifth, and sixth, which means that with a piece of paper and a bit of imagination, we've already visualized the first 6 dimensions of our reality. But wait, some of you might be thinking, wasn't it arbitrary for me to place the dinosaurs line outside the plane of my paper? Couldn't I just have easily placed a point at the center of the paper